We stand at the crossroads of energy demand and environmental crisis. Conventional energy sources strain our climate, while renewable options like solar and wind struggle with storage, intermittency, and infrastructure. But what if the answer lies beneath our feet, in our farms, in waste long regarded as useless? Manure and urine, often ignored and often despised, could become powerful tools in creating clean, sustainable energy. This video explores how these byproducts can be tapped, the science enabling their conversion to power, the challenges, and the promise they hold for the future. Before we proceed to the video, don't forget to hit the like button and ring the notification bell so you never miss our upcoming videos. Why waste matters. Every day, billions of animals produce tons of manure. Simultaneously, humans generate urine in massive volumes. Traditionally, these wastes are disposed of, spread across land, or processed in municipal treatment plants. These practices release greenhouse gases such as methane, nitrous oxide, and ammonia. They also carry nutrients that, when handled improperly, contribute to pollution in waterways and soils. If instead we treat manure and urine as resources, the environmental burden can transform into environmental opportunity. Manure, rich in carbon, organic matter, fats, proteins, and carbohydrates, is an excellent substrate for anaerobic digestion. Urine contains urea and nitrogen compounds that can be converted into ammonia. Ammonia is a fuel, a fertilizer, and a chemical feedstock. The energy and nutrient content of these wastes are substantial, but harnessing them requires correct technology, logistics, and acceptance. Biogas from manure. The science and application anaerobic digestion is the process by which microorganisms break down organic matter in the absence of oxygen. Manure, when placed in sealed digesters, becomes food for these microbes. The digestion produces biogas, primarily methane and carbon dioxide, along with small amounts of other gases. The methane component burns, powers generators, heats water, or can be purified into biomethane, usable wherever natural gas is used. On-farm digesters already exist worldwide. Large dairy or pig farms benefit most because they generate enough manure to yield meaningful volumes of biogas. The byproduct, called digestate, retains nutrients, allowing farmers to use it as fertilizer in place of synthetic fertilizer. This closes a nutrient loop and enhances soil health. However, smaller farms or dispersed waste sources face challenges. Transporting manure is heavy, costly, and can counteract some environmental gains. Digesters need careful maintenance, ensuring correct temperature, appropriate moisture, and microbial health. Capital investment is high, yet innovation is reducing costs. Modular digesters, mobile units, community digesters serving multiple farms. Urine to ammonia and energy urine may seem less promising because it is mostly water, but it is rich in nitrogen, urea primarily. When urea breaks down, it produces ammonia, which can serve multiple roles, as direct fuel, as feedstock for hydrogen, or as fertilizer. Electrochemical cells, EC, can extract ammonia from human urine. In trials, synthetic urine processed via EC achieved ammonium flux of about 384 grams of nitrogen per square meter per day, with approximately 61% current efficiency. Real undiluted urine yielded approximately 275 grams per square meter per day, approximately 55% efficiency, at about 12 to 13 kilowatt-hours per kilogram of nitrogen removed. Microbial fuel cells provide another option, energy production simultaneous with nitrogen recovery. In one study, an MFC using urine achieved ammonium recovery rate of 3.29 grams of N per day per square meter and energy surplus of 3.46 kilojoules per gram N recovered. There are efforts to use recovered ammonia in fuel cells or generators. Ammonia can act as a hydrogen carrier or be burned directly in specialized systems, releasing no carbon if the process is powered by renewable electricity. Environmental and economic impacts. Using manure and urine for energy can reduce greenhouse gas emissions significantly. Methane from manure that would otherwise escape into the atmosphere is captured and used. Ammonia production from urine can replace Haber-Bosch production, which is energy-intensive and reliant on fossil fuels. Nutrient recovery matters. Nitrogen and phosphorus from urine, if not captured, end up in water bodies, causing eutrophication and algae blooms. Capturing those nutrients helps both pollution control and agriculture, because recovered ammonia or fertilizer can return to fields. Economically, these systems can offer returns. Farmers save on energy and fertilizer costs. Waste treatment costs for municipalities or farms can decline. New industries could grow around system construction, maintenance, and operation. Especially in rural or off-grid regions, these waste-to-energy systems may provide energy stability. Case studies and data: electrochemical ammonia, extraction from real urine, flux of approximately 275 grams of nitrogen per square meter per day, 55% current efficiency, energy input approximately 13 kilowatt-hours per kilogram N. Microbial fuel cell urine system, 3.29 grams N per square meter per day recovered, energy surplus 3.46 kilojoules per gram N. On the manure side, many agricultural biogas plants provide steady performance, though exact data depend on scale, feedstock composition, and climate. Digestate also has value as fertilizer, reducing synthetic fertilizer use and its environmental costs. Challenges and limitations. Technical challenges. Digesters require precise control of temperature, pH, microbial populations. Transport of waste or processed residuals adds cost. Systems for urine separation and storage are underdeveloped. Ammonia extraction is energy-intensive and needs membranes, stripping absorption units, or catalysts. Health and sanitation. Human and animal waste carry pathogens. Systems must ensure pathogen kill or separation, odor control, and safe handling. Regulatory and social acceptance. Laws may not recognize waste-derived fuels. Permits may be complex. People may resist odors or stigmas. Public education is essential. Economic scale and infrastructure. Small, dispersed farms may lack scale. Utilities or governments must support infrastructure. Initial capital costs, maintenance, and training are significant barriers. Future prospects. Innovation is accelerating. More efficient anaerobic digesters, mobile models, and community-shared digesters. Urine separation toilets and on-site treatment systems are being developed. New electrolytic methods reduce energy input for ammonia extraction. The scale will rise. Pilot projects in rural and urban areas will prove models. Integration with other renewable systems, solar, wind, biomass, will build hybrid energy systems. Carbon credits or environmental markets may provide incentives. Policy frameworks must evolve to facilitate permits, subsidies, and standards. Manure and urine are more than waste. They are underutilized resources rich in energy and nutrients. When processed properly, manure can yield biogas that powers farms, homes, and communities. Urine can yield ammonia, fuel, and recover vital nutrients while reducing contamination. The challenges are real: technology, infrastructure, acceptance, and cost. But the examples already in operation, the data emerging, and the environmental and economic incentives all point toward a future where waste powers much of our energy. If we commit to developing these systems, supporting innovation, and changing perception, manure and urine could truly help power the future. If you enjoyed what you saw, don't forget to hit the like button and ring the notification bell so you never miss our upcoming videos. Your support means a lot to us. Take care until the next one, and feel free to drop a comment sharing your thoughts. See you soon.